Okay, so everybody, thank you very much for coming to the seminar. It's a pleasure to introduce Klas Modin from Chalmers University, University of Gothenburg. He's going to be speaking about Zeitlin's model for ideal hydrodynamics on the sphere.
Okay, thank you very much, Vincent, and thanks for inviting me to give this seminar. So let me just say something. My background is in numerical methods for Hamiltonian dynamics. And then I did a postdoc with Boris Hessin in Toronto. And then I got more into fluids, of course. And then about 5-6 years ago, something like that, together with Milo Viviani, we started a PhD project. And then this is sort of what I'm going to talk about today, is essentially what we started with Milo Viviano, who's now a postdoc at Scuola Normale in Pisa. So, and the talk is about this truncated model of the 2D Euler equations on the sphere, which is due to Zeitlin. He came up with this about 30 years ago, about 30 years ago. So I'm going to explain quite in detail, actually, how this model looks like. And what is nice with it is that it captures all the geometry of the 2D Euler equations. And when I say all the geometry, I mean the geometry from the point of view of Arnold, meaning that the equations that you see can really be interpreted as some geodesic equation involving the transformation group. So I'm going to explain that, and then I'm going to show you how how various numerical experiments that we've done with this model, and I'm going to try to convince you, if you like, that this is an interesting model to look at. Okay, so let's continue. So as I said, everything I do here, everything I've ever done related to the Zeitlin model is together with Milo Viviani. So I'm going to start this talk by showing you some videos, essentially, some numerical experiments that we've done. And then throughout the rest of the talk, I will try to explain how we did these simulations, what you actually see, okay? So first of all, before I begin, everything you see will be on the sphere, okay? And we're using, when I visualize something, I'm using spherical coordinates. So I map the sphere to a rectangle. It doesn't mean that we use spherical coordinates at all in the method. We very much preserve the geometry of the sphere, but just to visualize things, we do it this way because it's easier to see on the screen.
But the models use spherical coordinates, right?
The model doesn't use spherical coordinates, no. If you mean Zeitlin's model.
Yes.
No, we're not relying on spherical coordinates in any way whatsoever.
It doesn't use spherical harmonics?
Yeah, spherical harmonics, yes, but not spherical coordinates.
Well,
yes.
Okay. Well, they depend on the symmetry of the sphere, so
yeah.
Attached to the round sphere. Yes, that's the point I meant. Conceptually, it uses the round sphere.
Right. Exactly, yes, it uses the round sphere, yes, exactly. Okay, so but just so you understand what you see when you see some moving image. Okay. And what is it we're doing? So we're interested in the vorticity formulation of Euler's equations. To begin, so on the sphere, like this is the Laplace Beltrami operator on the sphere. This function here is called the stream function. This is the vorticity function. And you have the Poisson bracket on the sphere, and these are the evolution equations like this. The dot here means time derivative. And then what Zeitlin models does, it sort of replaces these equations with a finite dimension model, where functions, and we're really using quantization theory. So functions are replaced by operators, and because the sphere is compact, we can do it with finite dimensional operators, so just matrices. So what we do is we replace functions essentially by unitary matrices, and then or Hermitian matrices. Sorry, skew Hermitian even. Sorry. So and n here, you should really think of the size of the matrix, the parameter n. You should really think of as the truncation index. So in fact, when you have an element W in SUN, it corresponds to n squared sort of degrees of freedom in your model. Okay, and you will see exactly how this comes about. But essentially, the point is that you replace these equations, which has some Lie algebra structure here with these Poisson brackets, replace that by some quantized model where this Poisson algebra structure is replaced by just the matrix brackets or commutator. And then the question is, of course, how do you go from these equations to these equations, and what do we mean with these quantized Laplacian? That's what I'm going to discuss. Okay, but before that, let me show you some experiments. So here is a video. Here I just generated some smooth initial data. And how did I do this? Well, I say that I want my initial data expressed in terms of spherical harmonics. And then I take up to, let's say, the first 100 spherical harmonics, something like that. And,
and N is 100, capital N is 100 in that case?
No. Okay, so no. Let's say the largest L value in my, when you have these spherical harmonics, you have the L and the M value. The largest L is about 100. Capital N is about, in all my simulations, it's either 512 or 1024. So that's about the size of the matrices. So about 1 million degrees of freedom. That's essentially the size of this, okay? And to create a simulation like this and run it, so this one that you show here takes about, let's say 24 hours, something like that on a computer cluster. Okay, let's hope this works out. So what you see is that you get this sort of typical type of motion. Oops, yeah, this can happen. And you start off with a lot of small sort of complicated vortex formation. What you see is the vorticity function, of course. But then they did some sort of weak mixing going on. So they mix into larger blobs, but you still have a lot of fine grain, sort of fine scale things going on, okay? But eventually it seems to somehow settle. And be careful now, how many blobs do we have? If you count them, we have 2 red ones. These are the positive ones, and then 1 blue one. So it's periodic in this direction. So this and this is.
So you identified the upper and lower sides, right?
So now this is the North Pole. So this whole line is 1 point, right? This is the South Pole down here. So this whole.
Oh, I saw something disappear up there and reappear at the bottom. That's just an accident?
No, that was just an accident. They cannot.
Okay.
Yeah. So but this side is identified with this side, of course.
Yeah.
Yeah.
Oh, okay.
Yeah. Okay. So this is sort of how it looks like when you start from this kind of randomly generated data that is very smooth. And we did this for quite a lot of simulations, and essentially the picture that you get is always like this. Okay. So and we run this even for very long. And we never saw that these sort of 3 blobs break up. Of course, there's a lot of background motion going on, this fine scale motion, but the generic blob formations, they tend to remain. We never saw that they break up more.
Well, they were in the initial conditions, right? Those 3 blobs?
So let's go back and look at the initial conditions. This is how it looks like.
Oh, okay.
Right?
Oh, okay.
But the initial condition encodes something. It encodes all the Casimir functions, right? So you're evolving all the time on the sort of level set of the Casimir functions. So it encodes something, and in particular, it also encodes total angular momentum, which is something that is conserved in these equations. So in this case, if you just
there are 3 blobs sticking there, 3, and then there's a 4th one or 5th one, but there's. Lighter.
Yeah, okay, but if you look at this carefully, let's go a bit forward, like just a little bit. You see, it quickly sort of becomes complicated.
Well, but they're still there. 2 of them are still there.
Yeah, so essentially, what you can say is that you have a lot of them to start with, and then the largest ones are typically the ones that survives, because they sort of merge with the other one. It's weak merging, and then in the end you get. Let's see if I can.
The rich get richer.
Yeah, the rich gets richer, exactly. So here you see you have 4. You have really 2 blue ones. And it's interesting that it remains, you have 4 for a while, but then eventually this one sort of gets captured in by the third one. And then the two red ones, they do not merge.
Right.
And
well, the 2 blues merged, right?
Yeah, so just 1 blue, yeah. And 2 red. And I mean, the simulation you see here only goes on for some time, but we have continued this very, very long, and I'll show you a simulation like that later on. And not much more happens after that.
Is the swirl of the red approximately equal to the opposite swirl of the red of the blue?
Yes, because the total, the sort of
total swirl.
Yeah, the total swirl is 0, right?
Yeah.
So
okay.
so in fact, so when you integrate over the vorticity, you always it's always 0.
Yeah.
So that's a condition we have on. I mean, for the initial conditions. Yeah. And this, of course, has to do with the fact that the vorticity comes from some velocity field, right? Some divergence-free velocity field, and it's really, that's the reason that you have that.
Has to be. It's topology.
Yeah, it has to be.
Right.
Yeah,
topology.
yeah, exactly. Yeah, exactly. Okay, but there is something encoded in the initial data. There's a lot of first integrals in these equations, and that's something I want to talk about, how this looks like for the Zeitlin model. In particular, one of them is total angular momentum, I said. And in this case, because the initial data is sort of randomly generated, we don't have any control over that. But let's do something different. So again, we generate random initial conditions, but we make sure that the total angular momentum vanishes. It's 0. Okay, so now we have special, it's still sort of randomly generated initial conditions, but they're a little bit special. The total angular momentum is 0. Let's see what happens. Keep track of the number of blobs. Okay, so in the beginning, it looks sort of the same. You get some mixing, and the red ones sort of. Now you're starting to see that there are 4, right? And not so much more happens after this. You get 4, but it doesn't do like in the last one that it merges to 3. It just continues with 4. And we did a lot of simulations with 0 momentum. You always end with 4, not 3. Okay. So here is just a little something that we're investigating now. This is seems to be closely related to integrability theory for a low number of point vortices. So if you take point vortices on the sphere, so those are weak solutions to the Euler equations, right? If you take point vortices on the sphere, if you take 3 of them, you always get an integrable system, right? If you take 4 of them, in general, the system is not going to be integrable. But if you take 4 of them and the total angular momentum is 0, then the system is integrable. These are well-known results. And in fact,
what about if you take 5?
If you take 5, it's not integrable, right? Okay. So you see,
for 3 it is integrable, and then for 4 or greater, it's not.
For 4 and greater is not in general, but for 4, it is integrable if the total angular momentum is 0.
Oh.
Okay, so there's some condition there.
For 3, it always is.
For 3, it always is, yes, on the sphere. Yes. Okay, so actually, if you go through those proofs, you see that, of course, you need to have sort of point vortices moving around. What we see here are certainly not point vortices, right? It's not vorticity isolated to just one single point, and it's not even moving towards this. I mean, you get the blobs, but then the shape of the blobs are not sort of changing too much. But they actually, if you take point vortex dynamics and you replace the delta pulses by some axisymmetrical blobs, and you keep the shape of the blobs, but you move them around, you still get the same integrability conditions. So sort of these results are independent on sort of the shape of the blob. So we think that that is sort of what is going on here, that you reach some, you reach some, I mean, the merging keeps on going, right? The ones that have the same sign, they keep on merging until you reach some part of phase space where the large scale motion is almost integrable. And then, of course, there are some quasi-periodic motions, so they never get close to each other. And then you're stuck there. So of course, it's a long way to prove that, but that sort of seems to be what is going on here in these experiments. And well, one thing that is sort of, if you look at the statistical mechanics theories for hydrodynamics, or the so-called statistical hydrodynamics originating from Unsager, typically those theories, they sort of predict that you reach some number of blobs. In the sphere, it's typically 4. And that those blobs sort of reach some steady state. But that's not what happens, at least not in this model. So if you run the same, I have the same initial conditions now. Unfortunately, this video is not color, it's in black and white, but it's the same sort of type of video. But now I run it much faster and much longer. What you see is initially some mixing, and then you get this sort of.
Oh, there's nice braiding. There's nice braiding.
Yeah, so you get this quasi-periodic motion, and this seems to keep on going. So there's something to understand here, I think. And of course, this is a Zeitlin's model. So you could ask, I mean, yes, okay, nice. But in what sense does this capture the dynamics of Euler? So that's what I want to discuss a little bit. So here are the questions. As I said, exactly how is the Zeitlin model related to Euler? I'll give you some answers to this in the sense that I explain what you see here. I'll try to explain exactly how we did these simulations, okay? And then a big question is, how accurate is it? And I mean, an answer that I can give already is at the fine scales, not accurate at all, okay? This model is not accurate at the fine scales. On the other hand, no numerical method is accurate at the fine scales if you're looking at the Euler equations. So normally what people do is that they introduce some sort of artificial viscosity or damping, either in the numerical method, and then it's called numerical damping or numerical viscosity, or sort of by adding it physically as, you know, modifying the equations so you get, but then you really have Navier-Stokes instead of Euler. But I'm interested in Euler, so I don't want to do that. I want to capture as much as possible of what is in Euler. Because once you introduce viscosity, you destroy all these nice geometric structures. Okay, so that's not what I want to do. So it's not accurate at the fine scales. On the other hand, if you ask questions about Euler that sort of don't care exactly what is going on the fine scales, then possibly this could be captured in the Zeitlin model. And then this next question, guess, is really related to this. Does it capture the right dynamics of the Euler equations? Well, I don't know, that's a big question. But at least it captures the right geometry, and the geometry is related to the dynamics, of course. So,
but what about asking, does it capture the fluid dynamics of nature? It looks like it.
Yeah, there are experiments like this. What I showed you here, you can do experiments like this with soap films, thin soap films, right, that are moving around. And then essentially you get the same type of behavior. You get blobs forming, right, and mixing in a complicated way. But it's hard to avoid some sort of viscosity or damping in those models.
Yeah.
Those, so
reality.
In that sense, yeah, exactly. So in that sense, Euler is not a good model of reality, right? Because because normally you have some sort of viscosity, at least in these experiments, right? On the other hand, you know, on the quantum level, I think I don't know this very well, but for example, for the point vortices, I think there are quantum models that capture these point vortex dynamics very well. So perhaps there is some quantum model that captures the Euler equations.
You're saying your computations fit with the quantum point vortice models?
No, that's not what I'm saying. I'm just saying that if you're interested in point vortex dynamics, then there are quantum models that where the dynamics seems to be described very well by point vortex dynamics. I'm not doing point vortex dynamics. I'm doing something else.
You have a reference for that?
Yes, I can send it to you. I don't have it
Okay,
right now, but I'll send it to you. Yeah.
I'd like to have that. Yeah.
Yeah. Yeah, and there's some nice pictures. I remember looking through those papers. It's a fairly recent work, actually. So I mean, Unsager, he published his work. What was it, in the 50s, something like that, where he predicted lots of things. I mean, there were two major things he did in that paper: one in 2D and the other in 3D. So he developed essentially statistical hydrodynamics in 2D, and then he gave some conjectures in 3D as well. And then it was not until now 2009 or something, I think, that this appeared now for the quantum model I was talking about in Nature by 2 groups. I'll send you the reference. I don't know them by heart.
Thank you.
And the other thing that I'm interested in is, okay, so you saw what we did. We used quantization theory, or Zeitlin did. He used quantization theory to obtain a sort of finite dimensional model for the Euler equations. And once you are there in this finite dimensional setting, you're really working with skew Hermitian matrices, skew Hermitian complex matrices. And of course, we know a lot about the structure of those matrices. So I mean, the whole theory of Lie algebras and so on, you can try to apply that to these equations to see what happens and see what you get out, and try to map that back to the Euler equation. And just to give you some hint of what I'm going to talk about, just the spectral decomposition. The spectral decomposition of a skew Hermitian matrix gives sort of interesting results. Okay. So here is another thing you can do, and this comes entirely from the sort of Lie algebra point of view. So once you have a skew symmetric matrix, and in fact we have 2 of them, because we have the vorticity matrix and we have the stream matrix as well that we get from the quantized Laplacian. So once you have these 2 objects, it's natural to take one object and project it onto the stabilizer of the other one. And then you get a splitting of your vorticity. Right? So we have the P all the time. This is canonical. It's just given by the Lie algebra structure that you have and the Hamiltonian. That's all it depends on, right? So we have this P and the W, and then we project the P onto the stabilizer of P. Sorry, we project the W to the stabilizer of P, and then we get a splitting. And this splitting captures some interesting things. So here you see the same video, but now in terms of the same simulation I did before, but now in terms of these components, WS, which is the projection, and then the residual part. And initially you see it looks like this. You can't say too much here. The only thing you can say is that they both look rougher than the initial data. And in fact, they are, because if you try to do this in infinite dimensions, it doesn't make sense in C infinity. You have to work at least in L infinity or some weaker topology to make this. You have to make this splitting in a weak sense. More on that later. Just show you the video. So what you see is after a while, it seems that this WR part is sort of capturing all the high frequency motion going on, whereas this part gets quickly very smooth. And then yeah, okay, sorry. Are you seeing this? You see the video?
Yeah, we see it. I see it.
Yeah. Okay. So so this looks now very grainy, right? And it's interesting to study the dynamics of the Zeitlin problem or the Zeitlin model in terms of these two matrices, WS and WR. That tells you something, because for one thing, if you want to reach an equilibrium, so a steady solution to the Euler equations, a requirement, if you want that equilibrium to hold at each level, at each scale, then the requirement is that WR is exactly equal to 0, right? So in fact, what this tells you is that W is equal to WS if and only if W is actually a steady solution. But the other thing is that if you're just interested in sort of steady solutions on the large scale, that somehow means that WR contains just uniform noise. And here it doesn't. It's not perfectly uniform noise what you see here, and that's sort of what drives the dynamics. It's what makes the dynamics going on. Okay.
But wait just a minute. There's something different about WS. The braiding of the red around the blue that was happening at a uniform speed before for the entire thing has now been slowed down to almost nothing. There's no braiding of the force.
Yes, you're right, because what we see here is not transported. WS is not transported. You see, it's not transported by any flow, like vorticity. That's why you see in vorticity. So it's something else. And in fact, it's interesting what happens, because you sort of see blobs appearing and disappearing and then reappearing again, right? But when they disappear, they typically pop up in some other blob later on. So somehow this is moving, moving vorticity from this picture to this one and back again and so on in an interesting way. I'll tell you a little bit about the other properties of this splitting. It has interesting properties. So just to give you a hint, there are two sort of natural norms or natural inner products here. It's just the Frobenius one, which in the infinite dimensional case corresponds to the L2 inner product. And it's the one given from the energy. So in the infinite dimensional case, that corresponds to H-1 inner product. So you can define that also sort of quantized version of that in the Zeitlin model. And it turns out that WS and WR are orthogonal to each other with respect to the Frobenius or L2 inner product by construction, more or less, because we do orthogonal projection with respect to that inner product. But at the same time, we have that WR and W are orthogonal with respect to the energy inner products. So there's a kind of reverse relation between them. And that's interesting. I'll talk more about that later. Okay, so this is my first part of the talk where I just showed you some experiments, and now I want to talk more about the model, how we arrive at this Zeitlin model. So I'll try to.
So wait, that last statement that W and WR are orthogonal is sort of like the WR is this random thing. So therefore, it's orthogonal to any W or something. It averages out.
No, that's not it. That's not it. Even from the start, they're orthogonal. Even here. So it's that WR develops into this random thing has to do. We have some inequalities for this, but it's related to the fact that the H1 norm increases. When you run this, when you along the
increases. Yeah.
Increases. Yes, increases. Yes, it's related to that. Okay. Anyway, so let me move to the iPad and see if I can show you some details on the geometry of this model. So where is it? Oops, that's wrong. Sorry. Cable. Okay, do you see my iPad? You can see the screen, right?
Yeah.
Yeah. Okay.
I like pictures better than formulae.
Yeah. Okay. Maybe I'll go back to the pictures.
I'm just kidding.
Yeah. Okay. So first of all, I want to tell you. I mean, you probably know this, many of you already, but I just want to recap a little bit. What is the geometry that I'm talking about? What is this Arnold point of view on the fluids? And I do it in a sort of generic way on a Lie group. And for now, you should really think of this Lie group as a matrix Lie group. It works sort of what Arnold, of course, did it. He did it for diffeomorphism, volume preserving diffeomorphism. So it's infinite dimensional, but I'll just do it in finite dimensions. So we start with some Lie group. It has an algebra, and then we also introduce some inner product on the algebra, right? So from this we get a either left or right invariant metric on the entire group by just using a group translation. Okay, so if we take two tangent vectors to the group, and then we translate them back to the algebra, and then we use the inner product on the algebra.
But you know, your Lie group is compact or not?
It's in general, no. I mean, certainly the diffeomorphism group is not, right? In this case, later on it will be, but that's kind of interesting in itself. How can you approximate the diffeomorphism group with something that is compact? And of course you can't. So the approximation has to be somehow weak. So anyway, what we're interested in now, once we have this Riemannian metric, we want to look at geodesic curves. Okay, so now what is the condition for a curve to be a geodesic? So it has to extremize something. It has to extremize the action functional. So in particular, I have this kinetic energy Lagrangian given by the metric. And then I integrate over time and I get this action functional. So I want the curve to extremize this functional. And then because of the right invariance, I can really write this functional in terms of the generator, in terms of the algebra, the curve of algebra element generating the path. Okay, I'm just using the right invariance of the metric, and then I write it in U. And then of course, how do you extremize this? You take variations of G. So if I take a variation of my curve G, you see there's a sort of complicated relation to U. So what does the corresponding variation in U look like? That's the first calculation we have to make. Okay, so let's take a variation G epsilon of G, of the curve G in the group. And then we just take, by definition, we take sort of our generator U of epsilon now, and we differentiate this with respect to epsilon, see what we get. Okay, so by just differentiating, we get these two terms, and then this one was just called U, if you remember. This is the original U we started for, and this is sort of the variation. This V here is what generates the variation. Okay, so you have the blue and the green. And then you continue this calculation, and you see that in the end, what the variation looks like, it looks like this. You sort of isolate the V, and you get some variation like this, where V is the algebra element or the curve that generates the variation. So this is, if you like, Arnold's lemma, just this little variation. In fact, I think it goes back to Poincaré. And once you have that, we can sort of differentiate the action functional, and then we get something like this. And we notice that, so by the way, this is interesting here, the bracket comes out. In this combination here, it turns out that you get the bracket. I did this calculation in the simplest case just for matrix groups. It's a little bit more complicated if you do it sort of not in coordinates, but you get the same thing, also in infinite dimensions. So you get a bracket coming out here. And that means that bracket is, of course, the infinitesimal adjoint action of U on V, right? So, and I need to isolate V to get the equations of motions. So I need to somehow find the transpose or adjoint operator of add U, okay? And in fact, I just do that sort of abstractly, and then we get the equations of motions, now expressed in terms of some element in the dual of the algebra. And to obtain this element, what I do is I sort of write the inner, remember we started with an inner product. So I write this inner product in terms of the natural pairing between G and its dual G star. And then I get the so-called inertia operator, right? And then A times U is just the momentum variable that lives in the dual. And then the equations of motion, the so-called Euler-Arnold equations, is a set of equations evolving on the dual of the algebra, right? And
so the A is defined by the metric you chose?
Yes, yes.
Okay.
Exactly. Or you can say that A defines the metric, yes. So these are sort of the abstract way of writing down the Euler equations, you know, from this perspective. And of course, what we've taken now is,
you know, in the compact case, you could take the metric to be bi-invariant. How does that, what additional identity does that give at the finite level? in these equations.
So if you take the metric to be bi-invariant, then U becomes M and add star becomes add. So this is 0. So the dynamics is trivial.
Huh.
Okay.
Okay.
So it means that whenever you start with, if you take like a compact group, for example, and you take the natural metric, you know, the bi-invariant one, you get no interesting dynamics.
Right. Okay. So then that, can I just say, you were saying you can't approximate the diffeomorphisms by Lie groups, let's say, but if you took funny left invariant metrics as the dimension goes to infinity, it might do something. You know, definitely not bi-invariant, but interestingly left invariant, like squishing in some directions.
Yes. Yeah.
That's
sort of, yeah, that's sort of, in a way, that's what happens. You're right. In a way, that's sort of what happens here. You're taking metrics that are not canonical. It's important that they're not canonical, right? So.
Oh, I see. Okay.
Yeah. Otherwise, you get just trivial dynamics, and of course, I mean, what we did now, we derived this from the geodesic point of view. So this is sort of from, if you like mechanics, geometric mechanics, this is the Lagrangian point of view. There's also a Hamiltonian interpretation, and the Hamiltonian interpretation starts already at G star, right? Because G star, so the dual of a Lie algebra, has a natural Poisson bracket. It's called the Lie Poisson bracket. And so it's constructed in this way, right? You have an algebra operation, and then you have something in the dual, and then D of this, if you identify the dual of the dual with the algebra itself, then you get this bracket here.
So no choice of a metric now.
So now we haven't specified any metric. Instead, what we specify is a Hamiltonian. So once you have a Poisson structure and you want to do Hamiltonian dynamics, the only thing you need in addition to the Poisson structure is the Hamiltonian, the actual Hamiltonian. And then it's related to this inertia exactly like this. So now we need A inverse here because the sort of dynamics now takes place in the M variables, in the dual variable. So this is another way to think of the Euler-Arnold equations, that is just a Lie Poisson system with respect to a specific quadratic Hamiltonian. Okay.
Yeah. Okay.
So now, what about the 2D Euler equations? So let me see exactly how this fits into the 2D Euler equations, and then we do the quantized equations after that. So, and in fact, I say 2D Euler, but all the geometry that we're interested in here is captured if you do this on a symplectic manifold. So I would say the natural generalization of the 2D Euler equations are sort of the Euler-Arnold equations on a symplectic manifold, or if you like, even the Kähler manifold. So I do it on a symplectic manifold just to see sort of what structures we are using here.
And this fits with David Ebbins' proof that it's globally well defined.
Exactly. Fits exactly with that. And you see that what makes 2D Euler special is exactly this, that you have a symplectic manifold. That's what makes them stand out from, at least from my perspective. I mean, maybe other people have other perspective, but my perspective is that the 2D Euler equations stand out exactly because there is a symplectic structure. So the way to generalize them is to look at symplectic manifolds. Okay, so we have a symplectic manifold, a symplectic structure here, and this manifold now is compact. Okay, and that's quite important. But doesn't mean that the group is compact. Of course, in fact, the group is infinite dimensional. It's the group of diffeomorphisms preserving this symplectic structure. So the symplectic diffeos. And then the corresponding
component of the identity, the component of the identity, right?
Yes. Let's say yes. We restrict it to the that's true. Yeah, let's do that. So I should maybe write 0 here or something to restrict.
Yeah. Okay.
Yeah.
Because you're flowing.
Yeah. We always want to somehow start at the identity, and we're flowing, so we can't leave that part.
Right.
So what is the algebra? The algebra consists of vector fields, of course, and those vector fields are exactly the symplectic vector fields. So those vector fields preserving the symplectic structure. So omega is the symplectic structure, is the closed 2 form. So it means the Lie bracket or the Lie derivative of omega along mu is 0. Okay, another way of writing this with Cartan's formula, because omega is closed, we can really write this condition like this. Okay. And then remember, when we do this, we need to work with the dual of the algebra. And then now we're cheating a little bit. We're in infinite dimensions. So we're doing this in a sort of geometric way, pointwise. We consider only the smooth dual, right? So we identify the sort of smooth dual of the vector fields with 2n minus 1 forms. Because that's sort of, once you have the integral, that's the natural way of pairing a vector field with something. Once you have an integral and a volume form. And if you're on a symplectic manifold, you always have a volume form, right? So we identify the dual, the smooth part of the dual with 2n minus 1 forms, okay? So in such a way that the pairing looks like this. So you take your vector field, you contract it with the symplectic structure, and then you take the exterior product with your 2n minus 1 form. This gives you a volume, a top form, and that you integrate over M. This is the pairing that we're using. Okay, but in fact, this is for all vector fields. Now we're interested in just the smooth dual of the subset of vector fields that are symplectic. So it means that the dual of this subset should be some quotient. And it's in fact this quotient via the Hodge decomposition. You see it's the 2n minus 1 forms modulo the exact 2n minus 1 forms. So the 2n minus 1 forms that are d of something. Okay, because if you look here, if you look in this formula here, and you look here, what it means for a vector field to be symplectic in terms of this formula, you see that whenever alpha is something exact, this just vanishes, right?
Yeah.
So that's how you sort of get this. So what have we done so far? Well, not so much. We identified the group, we identified the algebra, and we identified the dual of the algebra, which is sort of where our momentum variable lives. Okay. And now we want to say something about the dynamics. So what is add? What is the add operator here? Well, it's just the Lie derivative. In fact, it turns out to be minus the Lie derivative. And this is some convention, I think, because the Lie derivative is the way I view it is the Lie derivative is sort of derived from the right action, whereas this add one, it comes from a sort of left action. So that's why I have the minus sign here. So we know what add is. Now we want its dual acting on a coset. So remember, the dual elements are now cosets. Okay. So how does it look like? Well, by definition, this must be, if I pair it with some vector field V, it must be this thing here, right? So then I just compute, I plug in what add U is. It's the Lie derivative. And because this pairing is very natural and nice, I can just move the Lie derivative here over to, and because U preserves the symplectic structure, I don't have to care about what it's sort of doing on this part here, on the omega. So I can rewrite this whole thing like this. And once I have it like this, the exterior product is of course natural. So I can just move it over with a minus sign to the alpha. Okay. And now what I've done, I sort of identified now what the add star is. The only thing is that the Lie derivative is within the coset. But in fact, because the Lie derivative commutes with everything with D, with the exterior derivative, I can move this Lie derivative outside. So in fact, it's well defined on the coset. Okay. So this is how my add star operator looks like. It's just the Lie derivative.
So U and alpha are like the viscosity and the vorticity. So vorticity and velocity.
So think of this coset as vorticity.
Okay. Yeah.
Think of U as the velocity field.
Yes.
For your Euler equations.
Yeah. Okay.
So it's here. It's a symplectic vector field, right? But in 2 dimensions, that's exactly what volume preserving is. It's just symplectic.
So now there's no metric to get Euler's equation.
So far, I haven't said anything about metric. There is no metric structure yet. It's just a symplectic manifold, right?
Yeah, but you have an Euler equation now, right?
Yes, yes, but I haven't told you what the Euler equations are yet. I just told you what add star is, and that we need to define sort of the Lie-Poisson structure.
Oh, that's
right?
the Lie-Poisson structure.
That's
now
the Lie-Poisson structure,
okay.
and now we need some Hamiltonian as well.
Yeah, okay.
We need some Hamiltonian, and that's where sort of the Riemannian part of this comes back in. So that's why you sort of need a Kähler structure or at least a Riemannian structure. So now we construct some kinetic energy or some Hamiltonian, and then to do that we need a Riemannian structure. Okay, and in fact from now on I will assume that M is Kähler, so the Riemannian structure fits together with the symplectic structure in this nice way. And then how do I construct it? So remember, I need to specify an inner product on the algebra. So now U is a vector field. I need to specify an inner product, and I just do it the natural way. I take my I take sort of my L2 inner product with respect to the Riemannian metric that I have, and I integrate it with respect to the volume form given by the symplectic structure. Okay, and then because M is Kähler, we have this relation between you have this triple, right? So you have the metric, the Riemannian metric, you have the symplectic structure, and then you have a complex structure as well, and you have this relation between them.
Where parentheses means the inner product. Comma parentheses means the inner product of the Riemannian metric.
This here?
Well, on the right. The parentheses and the comma means the Riemannian metric. No, that's just that's the symplectic form applied to the.
Yes.
Okay.
Yes.
Yeah, okay.
Symplectic. It's a symplectic structure, so it's a two form,
okay.
right? So it takes two
okay.
vectors.
Okay. Thank you. Yeah.
I could have write contraction. Maybe the right thing would have been contraction U, contraction.
No,
J,
this is right. I was just have trouble with formulae. Okay. Okay.
Yeah. Okay. Yes. Okay. So so where do I want to go with this? Yeah, I just want to identify what this inertia operator is. Remember, we need that to sort of write down the equations. So I start with this. So far, it's fine. I use the fact that M is Kähler now, and then what do? I write it exactly as I said in terms of a contraction instead. And now I can use contraction of the symplectic structure because of this formula here. And then there's I move this thing over here, right? Then probably there's a minus sign going away here, so I move it here. And now I have isolated my U, because if you look at the pairing, it exactly contains something like this. Let's look at the pairing. Where is it? Easy. So in fact, this I have now isolated my U, and from that I just read off what the inertia is operator. So A on U is in fact exactly this thing. Remember, it's a coset, so it's defined up to something exact. It's in 2n minus 1 form defined up to something exact. So once I have that, I get the Euler equations. They are like this. In terms of the cosets, I just write them like this, and the relation between the vector field and the momentum coset is this one, given by the inertia operator. This is so sort of how these equations look like when the algebra that you're given, or the group that you start with are the symplectomorphisms. Okay, so let's see what's next. Yeah, so of course, this is not the vorticity formulation, because vorticity is not a coset of K2n minus 1 forms, right? So we need to somehow identify this with vorticity functions. That's the next step, okay? And to do that, I really have to do a little bit of a restriction. I have to say that the vector fields we're working with are Hamiltonian vector fields. And sometimes this is a restriction, sometimes it's not. Depends on the first cohomology of your manifold. So on the sphere, for example, I can always do this. Every symplectic vector field corresponds to some Hamiltonian. In general, there might be something, some harmonic part in between there. But if I can do this, I say that I'm just now looking at symplectic vector fields that are generated by some Hamiltonian. And this Hamiltonian is, of course, a smooth function on my manifold M.
Well, if I may say something, I think most fluid discussions are incorrect about the treatment of the first cohomology group in dimensions 2 and 3. They sort of ignore it. And this is very similar to this assumption. It's just, this assumption is natural and prominent in this discussion. And it's sort of suppressed in 2D and 3D, in my opinion. Because you could always pretend, oh, I meant to say everything is zero. You know, that's sort of what is like that. So now you have to be careful, because this is.
I think you're right. I think you're right. Typically, I mean, the way this is normally done, if I may, is you start with the Euler equations, you apply curl, and you say, oh, it's the same equation.
Right. Yeah. But
which sometimes it is, sometimes it's not.
Well, and the Biot-Savart law produces a homologically trivial vector field. So, you don't have to say anything, but you know, it's an implicit assumption. It's not explicit, but here it's you have to do it. Right.
Yeah. Yeah. So you see, if you leave it at this, you're fine, right? You don't have to worry. But now we want to get to vorticity, and then I have to restrict my vector fields a little bit. I have to do it like this. In my case, on the sphere, it doesn't make it's okay, right? So I'll just assume that it's okay. And of course, how is this defined? Well, this is what it means to define a Hamiltonian vector field. This is the relation between the vector field and the Hamiltonian, right? So in the Keller case that we have here, you can also write it in terms of the gradient, which uses the metric, and the complex structure, just like this. Okay. So what do we do now? Let's see. What do I do now? Apply D, I said. Apply D where? Sorry. Sorry. Yes, apply D to this. Okay. Apply D to this, the relation between the vector field and the momentum. Okay, so I apply D to this equation. And then, of course, I don't have to care about the coset any longer because the exact part went away, right? So then I have this equation. And D alpha, what is it? It's top form. So D alpha is a top form. So let's use the volume form that we have to identify that top form with a function and call it omega. That's our vorticity. Okay. So now here I have up to just, you know, normalization with the volume form, I have here vorticity. And in fact, this equation then turns into this equation, which gives you a relation between the vorticity and the vector field, your symplectic vector field, okay? And what am I saying next? Well, I'm saying, remember what I'm saying, U here is Hamiltonian, generated by some Hamiltonian. That Hamiltonian is exactly the stream function. So in fact, what I have derived now is the relation between the stream function, which is the Hamiltonian generating your vector field, and the vorticity function, which is just a representation of this coset here, assuming trivial first cohomology. Okay. And now I can just rewrite these whole equations. Everything is sort of natural because I'm always dealing with symplectic vector fields, and sort of everything I'm using here is the symplectic form. It's a transport here. It's still going to be a transport equation. So I'm just transporting vorticity, just like I did before. This is the vorticity formulation of Euler's equation, because of course the Lie derivative of a Hamiltonian vector field on a function is nothing but the Poisson bracket between the function and omega. Okay. So let's recap a little bit what we have. One thing I didn't say was that when you do this identification here, omega always integrates to 0 by construction. So in fact, omega belongs to this set that I called C infinity 0. It means it integrates to 0 with respect to the symplectic volume form. The volume form given by the symplectic structure. Okay, so when you take and remember, this is our dual, right? So now there is another way of sort of thinking of the algebra. Either you think of it as your symplectic vector fields or Hamiltonian vector fields, But then you also have to specify, instead of specifying the vector field, you can just say, okay, I'm just interested in specifying the Hamiltonian. And the Hamiltonian is defined up to sort of just a constant. So this is again a quotient. But now, so here you have a quotient here and not a quotient here. When you do this identification, it's the other way around. You have a quotient here, it's a small quotient, but anyway. And then here, there's no quotient. This is natural. This is sort of how it comes out geometrically. And then remember, we computed the add star. It looked like this when you were acting on the cosets. And then when you move to vorticity, it's somehow much simpler. It just looks like this. It's just a Poisson bracket. So, so what have we said? We said just what we have derived is that the Euler-Arnold equations in this setting is the vorticity. Remember, we're on symplectic manifold, so you can argue if you should call this vorticity formulation. But if you restrict to the two-dimensional case, it's the vorticity formulation of the 2D Euler equations. It looks like this. And the other thing that I didn't say is, you know, there's a Poisson bracket coming out here. This is a Poisson bracket on the finite dimensional manifold, so on M, right? How is it related to the Lie Poisson bracket on the infinite dimensional dual of the algebra? Okay, it's related like this. So the infinite dimensional Lie Poisson bracket takes two functions defined on the dual of the algebra and gives another function defined on the dual of the algebra. Okay, so of course this is infinite dimensional. This is a little bit complicated because what we're doing, we're identifying the dual of some infinite dimensional space of the dual of itself with the algebra itself. So it's cheating a little bit. But anyway, formally, this is how it looks like. So it's related to the finite dimensional Lie Poisson bracket like this, with just the integral and then integrating over, multiplying with the vorticity function. Of course, there should be an omega n here as well. I need to integrate with respect to volume 4. Okay, so here is what we have again.
Why are you integrating over S2?
Oh yeah, it should be M there. Sorry, it's just because I'm so used to it that everything is just S.
You're secretly on S2, okay.
Yeah, exactly. Secretly on S2, yeah. Because that's really what we can do computationally.
Yeah.
That's really where the quantization works out explicitly in the way we want.
So you're thinking, you don't think of Euler as fluid motion, you think of it as this flow on this symplectic manifold S2 associated to the symplectic structure.
Yeah, yes, exactly, yes. I think this is the right way to think about it when you discuss this Zeitlin model.
Right.
Yeah. So again, this is what we have. So we sort of first.
Excuse me, if it were the two torus, you would still be working with the Hamiltonian subfields, right? Inside the area preserver.
Yes. And in that case, it's not trivial, right? In that case, it's not trivial.
It's what?
The cohomology group, the first cohomology there is not trivial. Right?
Yeah, exactly. So you're restricting the kind of motions you're allowing.
Yes.
That means there's no circulation in either direction.
Yeah. Exactly. Yes, something like that. Yeah, you're right. In fact, so just a little history. When Zeitlin did this, he did it on the two torus, because somehow it looked like it was simpler to do there, because then basically everything is based on the two-dimensional Fourier transform, which is very simple because you have this tensor product structure on the two torus. But in fact, what we realized while working with this, I don't know, maybe he also realized, was that on the sphere it works much better. And maybe I'll come back to
numerics is better, you mean, or what?
No, the geometry is much simpler and nicer.
Oh, okay.
But that also means something for the numerics. So I can tell you what it means. It means that in the quantized model on the S2, we exactly preserve the SO3 symmetry.
Oh,
right. On the quantized model on the torus, it's not exactly preserved. It's sort of discretely preserved, but there's no continuous symmetry group.
Yeah.
And this is a deep sort of geometric reason for this. And one way of looking at it is because the generators that generates the isometries on the sphere are sort of part of the spherical harmonics. Whereas on the torus, you really need to the generators are these functions x and y, if you like, you know, and to get the Fourier series of those, you need infinitely many terms. That's one way of sort of explaining why what is happening. I think I talked to some people that know a lot of Kähler geometry. They have a much deeper understanding of this. So this is sort of there's some deep geometric reasons for why it works better on the sphere than on the torus. Okay, but from how I understand it is exactly what I said, that actually the isometries are sort of part of what we bring with us in the Zeitlin model. We exactly preserve the symmetry group. Okay. So what else? Yeah, one thing I didn't say, once you have such an Lie Poisson system, it's always some sort of, it's like a transport equation. So it means you always evolve on the orbits, on the co-adjoint orbits. So on the group acting on the dual of the algebra. So this means that you have a lot of conservation laws. And in the two-dimensional Euler equations, this is sort of what gives rise to the infinitely many Casimir functions. And if you work in the sort of smooth category, like I do here with smooth functions and smooth diffeomorphism, we know that these orbits are quite complicated. I think the talk last week was essentially about this, right? Francisco Torres, didn't he talk about exactly what you can reach and sort of when you act with the diffeo on some function, with the volume preserving diffeo. So these are complicated. And it turns out that in the Zeitlin model, it's easier to understand this.
So was Zeitlin a student of Vishik?
Sorry, who?
Was Vishik.
Who was a student of Vishik?
Zeitlin.
I don't know who was his supervisor.
Okay.
Sorry, I don't know. Yeah, I guess we could find out.
Because Vishik was talking about this at IHES 35 years ago or something. I mean, about Euler on the torus and approximating it by finite dimensional Lie algebras. But, you know, it wasn't as complete as what you're saying.
So perhaps, are you saying that I shouldn't call them Zeitlin? The Zeitlin?
No. I'm not saying that. I'm just, I'm just, they're two Russians and maybe they're colleagues in some sense.
Yeah. Very likely, yes.
The idea was that because it was something on the torus and there were finite dimensional approximations to Euler dynamics on the torus. But,
okay, thanks for that comment. I'll look it up. Maybe I'll ask Vladimir.
He was the organizer of this centenary for Rocklin. Vishik may be his first name or his last name. I can't remember.
Okay.
I think it's his last name.
Yeah.
He's a famous mathematician.
Yeah. I know the name, of course. Yeah.
Okay.
Yeah. So that's Euler for me, 2D Euler, right? So now let's go to finite dimensions and discuss Zeitlin's model.
Yeah.
And so let's see. I have half an hour, right? I will not manage in half an hour. I'll try to do as much as I can. So what is the aim? The aim is a spatial truncation of vorticity that preserves this Euler-Arnold structure that I just explained to you. So essentially, we want to replace
Lie Poisson plus energy.
Yes, exactly.
That's what you mean by that, right? So Lie Poisson plus the energy.
And the energy should be quadratic. Yes.
Yeah.
The energy should be a quadratic function. Yes. So what is needed? Well, what is needed to define this is exactly what you said, right? We need some Lie algebra structure, and we take the dual of that, right? And in this case, for the Euler equation, it turns out that the Lie algebra structure, you can think of it either as Hamiltonian or symplectic vector fields, or you can think about it in terms of the Poisson algebra of smooth functions, right? So this is our sorry, yeah. So this is our sort of Lie Poisson space. That's one thing we need. The other thing we need is exactly what you said. We need a Hamiltonian. And another way of thinking of this is we need a Laplacian. Because if you remember, once we're on the vorticity level, the Hamiltonian is sort of defined in terms of the Laplacian. So we need a Laplacian. So those are the things that we need. And what is the idea? The idea is to sort of use quantization theory, which is a systematic way, if you like, to replace what is the idea of quantization, at least from my perspective. The idea is you take a set of functions defined on some domain, on some manifold, and then you try to replace this Poisson algebra of functions with an algebra of matrices, you know, so in such a way that the Poisson bracket sort of somehow is approximated by the matrix commutator. I mean, so in general, these are operators, right? If your underlying manifold is not compact, you cannot hope to make this finite dimensional. But because we're sort of on a compact manifold, we can hope to make this on the finite dimensional spaces. So this is what we're aiming to do: replace vorticity functions by skew Hermitian matrices. Okay, in such a way that the Poisson bracket is approximated up to some level by the matrix commutator. And when I write H bar here, H bar is really, so the quantization parameter, if you like, Planck's constant, is really just 1 over n. Remember what n is, this is the size of the matrices.
Your H bar looks like trace, which I've been reading all the last 2 minutes.
Right.
ER.
Okay, sorry, it's not trace, it's H bar. Yeah, okay. Right. So in fact, yeah, and in fact, we can take special unitary algebra because remember we have the 0 here, so it integrates to 0, and that corresponds to the fact that the trace is 0. So we can put an S here. Okay. And then we have this sort of structure where the Laplacian. I think of the Laplacian as going from this space here, the quotient smooth functions defined up to a constant. So these are Hamiltonians, if you like, to vorticity functions, which are functions that integrate to 0. Okay, so I think of the Laplacian as a natural sort of operator between these spaces. So I need somehow a discrete or a quantized Laplacian. Okay. How this is constructed, and in fact, how this entire quantization scheme is constructed, goes back to Jens Hoppe, who did it in his thesis in the 80s. And this Laplacian, he did also some work with Yau. So it's Hoppe, and I call it the Hoppe-Yau Laplacian.
What's the name of the thesis person?
Jens Hoppe is his name. I don't know the name of the thesis, but it's you can download it from his webpage.
Yeah, how do you spell it?
Hoppe.
Oh, thank you.
So he probably did a postdoc or something with Yao. I don't know, but he was there for a while, and now he's in fact in Sweden, at KTH in Stockholm. Okay, so and then somehow we want to replace these Euler equations with this sort of quantized version. That's the idea. And this is some infinite dimensional Lie Poisson system with a Hamiltonian here. Remember, this Hamiltonian is defined in terms of Laplacian, because to get the stream function, I need to invert the Laplacian to solve the sort of Poisson problem. In the same way, if I have a quantized Laplacian, I get a stream matrix, and then the Hamiltonian is defined in terms of vorticity and the stream matrix, just like this. So this will be our Hamiltonian. So always whenever I trace of something, you should think of this really as a sort of L2, or if you just like an integral, corresponds to the integral. Okay. So
delta sub n again.
Sorry.
Delta sub n of p equals w. What's delta sub n?
Yeah, that I want to explain to you. I haven't said. For
okay.
now, we need to construct this object, right?
Oh, okay.
In order for these equations to be well defined, we need to construct this object. The other thing we need to do, we need to show how we go from vorticity function to vorticity matrix. This is sort of the quantization. I haven't told you how this looks like. That's what I'm going to do now. Okay. So we need, but so far, let's just see what we want from this. So we have a group here in the infinite dimensional case. We want to replace this by SUN. Okay. We have an algebra consisting of either symplectic vector fields or this space here of Hamiltonian functions, and then we have a corresponding algebra here. It's just the Lie algebra of this Lie group. Okay. And then because this sort of Lie algebra is compact, as you said, we have a killing form. It's enough that it's semi-simple. We have a killing form, so we can identify the dual with the algebra itself in a canonical way. So I'll do this. It just makes the things a little bit easier. And if we do this, then the add star operator is in fact just the commutator. Okay. Then we have an inertia operator, which is the Laplacian here, and it's some sort of quantized Hoppe-Yau Laplacian. Okay, so that's what I want to talk about now. What is this Laplacian? How do I construct this? So how do we obtain explicit quantization on the sphere? So what we do, let's sort of start at the finite dimensional setting. So we take a representation of the algebra SO3 in UN, okay, in the skew Hermitian matrices N for some, let's say, large N. In physics, this is called a spin S equal n-1 divided by 2 representation of SO3. Okay, then we want these generators to fulfill this requirement. So they're fulfilling the algebra requirements of SO3 up to this Planck's constant here. Okay. So I did it for 1, 2, 3, and of course it continues in a cyclic way. Okay, and what Jens Hoppe gives us, he actually gives us this representation explicitly. Okay, so he gives us these matrices X1, X2, and X3. And they have a nice feature, namely, if you look at their spectrum, the eigenvalues, it's contained in the interval -1 to 1, and it's equidistant in that interval, okay? And it sort of gets closer and closer to the interval -1 to 1 as you let n grow. Okay, so it's equidistant, and it essentially, as n goes to infinity, becomes the interval -1 to 1. All these matrices have that property. So now, once we have this representation, we can think, is there a way to construct the Laplacian on the infinite dimensional space from the Poisson structure, on S2? And there is such a way. And the way you do it is like this. You start with some generators, and these are in fact, again, a representation of SO3. And the generators are just the coordinates. So you think of S2 as embedded in R3, and then you have these coordinates functions, X1, X2, X3. That's a representation of little SO3. Okay, it fulfills these requirements here. And of course, by construction, the range of these functions is -1 to 1. So you should really think of the eigenvalues here, and this is sort of part of quantization theory, right? That the eigenvalues corresponds to the function values. When you take the classical limits, then the sort of eigenvalues that you get corresponds to the values that a function can take. And already this sort of indicates that we're on track. Something seems to be right, okay? And now I'm still talking about the continuous sort of infinite dimensional normal Laplacian, Laplace-Beltrami operator on the sphere. And it's generated like this. So once you have these generators, you just take your brackets and you apply it twice, and then you leave this slot open for some function. This, in fact, gives you the Laplacian. Okay, so it's generated from these generators for the isometries, if you like, on the sphere.
So that's the part that you added earlier, that this version preserves the symmetry of the sphere.
Yes, exactly. You're right. This does not happen on the torus. It's not as simple as this.
Yeah.
So something special happens on it. And if you think about it, in fact, the only thing that is different on the torus and the sphere, because you can work out the quantization on the torus as well. The only thing that is different is the Hamiltonian. The Poisson structure is the same. It's sort of fixed, right? It's just the algebra structure. So what is different is, in fact, the Hamiltonian, which is sort of the Laplacian. That's the only thing that differentiates the dynamics in this quantized regime. The only thing that differentiates the dynamics on the sphere and the dynamics on the torus is the choice of the.
So this is HT Yao, not ST Yao, right?
It's ST.
Oh, it's ST Yao? Oh, really?
Yes. Yeah.
So what's he doing in this field? Oh, it's
the paper. Yeah, so I don't know. I mean, I suppose Hoppe was there as a postdoc or something.
Okay.
I mean, this was in '98.
Okay.
I don't know if that tells you anything, but yeah.
Okay.
So once we have this formula, right, and we know that these generators somehow corresponds to these generators, it represents the same algebra, right? And they have very similar properties in terms of the spectrum here and the range here. So we just construct the Laplacian in the same way, you know, just plug in this formula. Of course, you have to take care that you get the right brackets here. So you have to divide by Planck's constant raised to the power 2, which is just n squared, in fact. So this is our Laplacian, okay. And here is the nice theorem, okay. The theorem is the following. The eigenvalues of this quantized Laplacian coincide with the first n square eigenvalues of the exact Laplacian.
Huh.
Okay. So amazing. The paper is very algebraic, and I'm sure it's completely obvious to them that this is the case. For me, it was not obvious. Maybe there is a nice geometric way of understanding this. I'm sure people in Kähler geometry that study quantization theory from this geometric quantization theory, where you start with a complex line bundle and so on, they probably have a good understanding for why this is the case. But anyway, this is a result.
Wait, so I'm lost. The L. Wait, there are two parameters. Before there was just one. So
yeah. So
these are, L runs from 1 to n or something.
Yeah. So L runs from. So L runs from 0 to n minus 1, right?
Yeah. Okay.
And then for each L, you have a number of m's that goes from minus L to L. This is how you sort of number the spherical harmonics, right? And the spherical harmonics are the eigenvectors or eigenfunctions of the Laplacian. So you see for each, so the eigenvalues only depend on the L. So for each L, this eigenvalue has multiplicity, what do you say, 2L plus 1. Okay, so the eigenspace has dimension 2L plus 1. So okay, and this is exactly the same.
This is just the obvious cutoff, so to speak. You might say.
Yes. Yeah.
Oh, well, is it the Galerkin projection of Euler equation?
It's not the Galerkin projection, because so that's another method, right?
No, it's another method. It's another name, but maybe the formula is the same.
Okay, so let me say it like this. Here is an idea. I want to come up with a numerical method for the Euler equations. Okay, so how do I do it? Well, I first work out how I write down the Euler equations in terms of the spherical harmonics components.
Yeah.
Right. People have done that. You work out how these equations look like. You take those equations and then you truncate everything above a certain L. So whenever L is larger than, you just take it away. You get some sort of finite dimensional motion, right, from that. That's not the same model. It's not the same model as the one we're using. That model will not preserve the geometry. It might preserve just some of the integrals, but certainly not this structure. Okay.
What about on the torus?
Not even on the torus. It will not preserve, because essentially what happens is that you're using the correct, if you like, the infinite dimensional algebra structure, and that wants to push frequencies. You know, if you take two high frequencies and you combine them, you get something with even higher frequencies. So it pushes frequencies out, right? And this quantized model sort of takes that into account, that you cannot push frequencies out, because what you do in the model then is you take these frequencies, you push them out, and then you just forget about them. And
what happens
that's not,
here?
What we're doing here is, if you like, we're modifying the Poisson structure. So we're twisting the Poisson structure a little bit. If you think of it in terms of the spherical harmonics, what we're taking is we write down the Poisson structure in the spherical harmonics, and then we twist it in such a way that it becomes finite dimensional. That's sort of one way of thinking of it. Okay.
Oh, I see. There's no Lie algebra associated to the Galerkin projection, you might say.
Exactly. There's no Lie algebra.
It doesn't satisfy Jacobi. You can formally write down a bracket, but it won't satisfy Jacobi.
No, it will not.
Okay.
Yeah, very, very good. Yeah, exactly. So now we have this nice thing. We have this nice Laplacian. And in fact, I want to sort of build my entire quantization just on this very nice Laplacian, right? Because what is the idea? Once you have this Laplacian, work out what the eigenvectors are of the quantized Laplacian, and then identify those eigenvectors with the spherical harmonics, which we know are eigenvectors of the infinite dimensional Laplacian, or the Laplace-Beltrami operator. Okay, so this is the idea. We sort of construct these eigenvectors for this operator. This is now an operator on SUN, remember, right? And then once we have constructed them, we use that to identify sort of the components of the vorticity in terms of spherical harmonics with a matrix. And then we have a mapping going in either direction, actually. If you go in the forward direction, so you go from here to here, you need to truncate. If you go in the other direction, it's some sort of lifting, where you lift some finite dimensional object and embed it in a larger space. So that's the idea, that this gives a mapping. So you first take your vorticity function, you express it in terms of your spherical harmonics, and then you just replace this basis of spherical harmonics with the matrices given as eigenvectors. Maybe I should say eigenmatrix, because this is really a matrix, right? What is the problem with this? Well, the problem is that the eigenspaces are not one-dimensional. So how do I know what the eigenvalues are for each L, but each such sort of eigenspace has some dimension. So how do I select this TLM? How do I know which ones to select? I need to pick a basis within each eigenspace. So let's address this. So here are so for each L, I have a corresponding eigenspace. It looks like this, right? So this eigenspace is of course unique, but how do I uniquely determine a basis so that I get the TLM? Okay, that's the question. So do I have only 5 minutes?
Yeah.
Okay, so I'll try to be
very
quick.
No, you have 5 minutes or more, at least 5 minutes.
Right, okay.
Lunch closes in an hour and a half. That's my upper bound.
Okay, right. Right. So, okay, I'll try to speed up. Sorry. So, so how do I do this? Well, let's start with a simple case when m is 0. Okay, and then just think about it in the infinite dimensional case.
Why do you need a basis anyway?
Because we need to we need a way to identify sort of vorticity functions with vorticity matrices. And the way, and we can express this vorticity in terms of a basis. So we do it on a level of the basis, and we just say that this sort of spherical harmonics basis has a corresponding basis in the quantized level, because both of these are somehow eigenvectors of either the real Laplacian or the quantized Laplacian. So this is sort of how we construct things. But then we get into a problem, because How do we uniquely define this? And by the way, this is not how Hop and Java is doing it at all. Instead, they're using the fact that you can express the spherical harmonics in terms of what is called harmonic polynomials, in these generators, x1, x2, x3. So multivariate polynomials. And then once you have that, you can take those polynomials, plug in the matrices, and then you get a new matrix. Problem is, if we try to do that numerically, I'll tell you why I don't want to do that later. Okay, I want to speed up a bit. But let's just first think about the simple case when m is 0. Okay, so what does this correspond to on the level of functions and harmonics? This means that your function is zonal, so it's constant on the longitudes. Okay, so whenever you have some function that is expressed in spherical harmonics, and all the spherical harmonics have index 0, I mean all the other coefficients are 0, then it's always going to be zonal. Okay. So what this means is somehow that it commutes, that these spherical harmonics commutes with this x3 generator, right? It just means if you rotate about the x3 axis, nothing happens. And this is an infinitesimal rotation about this axis. So the corresponding quantized thing then is that this TL0 should commute with x3. And x3, Jens Hoppe gave us x3, so we know what it is. And in fact, it's diagonal, okay? And if you look at this construction here, you see that this quantized Laplacian, it maps diagonal matrices to diagonal matrices.
Excuse me, what does x3 do on the sphere symmetrically?
x3 generates rotations about the third axis, about the z-axis, right? So you have these x1, x2, x3. Each of them corresponds to rotation about x, y, and z axis, okay. 1, 2, or 3 axis. Yeah. But infinitesimally, right? So what did I want to say? Yes, so it maps diagonal to diagonal. So we can sort of restrict the problem first to just diagonal matrices and solve this problem, right? For each possible L. And then each of these subspaces in the subspace of diagonal matrices it's a one-dimensional eigenspace. So then it's unique, okay? And in fact, in general, it turns out that this Laplacian maps so matrices that are M diagonal, meaning they have something on the mth diagonal, but nothing sort of in between. 0 here, 0 here, 0 here, something here. And then you get a new matrix which has exactly the same structure. Okay. So by restricting to these sort of subspaces, we get uniquely what TLM needs to be. And you see, then we also have a nice interpretation of what M means. It means which off diagonal you're on. So M corresponds to the sort of diagonals of your matrix. That's what it specifies. And then then we have only, if we restrict to these subspaces, you have only one-dimensional eigenspaces. So you can solve this uniquely. And numerically, this is amazing, because what it means is that when we solve this, sort of one way of sort of constructing this basis is just to solve this problem numerically, okay? So we get the TLM. They are, first of all, these are sparse matrices. That's interesting in itself, but they are computed by solving a sparse eigenvalue problem, which has only size n minus m. So you see this operator, if you express this as a matrix, it's sort of an n squared times n squared matrix. It's enormous. Oh, you're muted, I think.
Yeah, I mean, this is like you reduce, the Poisson problem usually is huge, and you're reducing it down.
Yes, so just the diagonals. Yes.
The square root of more than the fourth root.
Yes, yes, I'm going down a lot. So this is numerically very good, because it means that we can compute this for quite large n, because nothing becomes n to the power 4 in complexity. Yeah. If you look at this from the beginning, it looks like everything is n to the power 4 complexity. Yeah. But it's not, in fact. Yeah. You see, in fact, you can solve this in just n square operations. So it's very fast. And if you're on a computer and you want to do this for n equal 1,000, it's a couple of seconds to do it. The original approach that Hoppe and Yao used, where you have these harmonic polynomials, then you get explicit formulas for the TLM. So that's nice. At first we thought, okay, that's very nice. We have explicit formulas, but they involve these Wigner 3J symbols of extremely high order if you want your n to be large. And to compute those Wigner 3J symbols accurately of high order is not easy. So we did that. There are sort of algorithms to do this. It took us, I think, Milo, if you're here, you can correct me, but I think it took about 2 months or something to do this on a computer cluster for n equal 1,000. So it saves us a lot to understand this sort of this from this perspective. Okay, so other nice properties of this sort of computationally nice properties of this Laplacian is that it's extremely sparse. So as I said, you know, it should be an n squared times n square matrix, but it only has n squared, or you know, the level size of n squared non-zeros. All the other elements are zeros. So it's a sparse matrix, but even more importantly, it's sort of by the structure of this matrix, you can explicitly construct a sparse LU factorization of this matrix, which means that you can think of this as the multiplication of two large but very sparse matrices, L, which is lower triangular, and U, which is upper triangular. And if you think about what that means we have the Gaussian elimination scheme already. So it's very fast to compute its inverse. So in fact, to solve this quantized Poisson problem, we can do that in only n squared operations. So that helps a lot. And so really, what is the computationally heavy part in the Zeitlin model? It's not solving the Poisson problem, which you might think originally when you look at it. It's in fact to do the matrix multiplications. Because remember, this matrix W is a full matrix. So when you do matrix multiplications that you need to compute the commutator, that operations requires n to the power 3 operations. That sort of algorithm requires that much. So that's the heavy part in these calculations. So let's see, where am I? Summary so far, okay. We have an approximation of vorticity via Zeitlin's model. And how do we do it? We start with some initial vorticity. We express this initial vorticity in terms of spherical harmonics. We truncate this, you know, so that we get n squared components. And then we compute the corresponding basis elements. And from that, we get the initial vorticity matrix. And then we when we follow the flow sort of Zeitlin's finite dimensional model with this initial condition, we also know how to solve this Poisson problem, the quantized Poisson problem. And once we've done that, we get some matrix at level t, let's say, at time t, and then we can construct back the corresponding vorticity function, but just taking the components in this basis. And this, by the way, because this is skew symmetric matrix, so skew Hermitian matrix, the eigen vectors are going to be orthogonal. So to get back this, we just take the trace with WT with a basis. We just project onto the basis to get the components. So this is sort of the numerics. This is how it works, like how you go do the entire thing. There is one thing I'm not talking about, of course, which is how you discretize the time. So that's in fact a very important question. I don't have time to discuss that, but of course you want to discretize in time such that you preserve the Hamiltonian structure. That means you need a symplectic integrator. So what Milo did in his thesis was to, well, he did a lot of things, but one thing he did was to develop a Lie-Poisson preserving time discretization of these equations. Okay.
So what does that mean?
So that means, so if you really think about this, you have some dynamical system, right? Evolving on a finite dimensional manifold, which has a Poisson structure. It's a Hamiltonian system, right? So now we're saying the flow, because it's a Hamiltonian system, the flow is going to be a Poisson map, or even more, it's going to preserve the coadjoint orbits. So it's going to be a symplectic map on the coadjoint orbits.
Yeah.
Okay. And then you can ask, I mean, I'm applying some numerical method. Somehow the numerical method is an approximation of the flow map, right? And I'm doing it sort of time by time, taking some time step, I approximate the flow map, and then I go forward like that. So a symplectic integrator means that the flow map your approximate map is also preserves the Lie-Poisson structure and preserves the coadjoint orbits. Okay, and then
Yeah,
once you have
mean?
that,
no, what does it mean? The Lie bracket on the discrete approximation.
Yeah,
what
but I mean, no, but okay. So I'm doing it like this. These are the flow equations. This is infinitesimal, right?
Yeah.
Okay, but the flow map you get. Let me draw something. The flow map you get. Let's call it phi. Right. That is going to be some, if your time step that you use is small enough, this is going to be some diffeomorphism, right, on your underlying manifold, which in this case is SUN, right? And in fact, it's going to preserve this the Poisson structure. How do I write this? Maybe I just write P here to say that, you know, the flow generated from this will be some at some, you know, specific time level will be a symplectomorphism, or will be preserve the Poisson structure. Okay.
Yeah.
So now I'm saying I want to approximate this. So I want to approximate this map. So I write tilde here to say that I approximate it. Okay. And this in general, this is also going to be a diffeomorphism. But in fact, I want this diffeomorphism to also preserve P. This is perfectly fine to say. I'm not doing anything infinitesimally. I'm just saying that the map that I'm using to approximate the flow is also going to be preserve the Poisson structure. And then once you have that, you can do something which in numerics is called backward error analysis. So you can ask the question, once I have my method, you know, it preserves the Poisson structure. Does it correspond to the exact flow of some modified Hamiltonian function?
But excuse me, how are you right? You can't write a diffeomorphism of a manifold on a computer. So what does phi sub h even mean?
Well, so okay, so let's take some simple example. Let's write.
No, just you could say it abstractly. I mean.
Yeah, okay, but I just want to show you a little bit.
No, I understand.
So here is some generic flow equation on some finite dimensional manifold. Let's say it's flat, right? So I can so there's like a linear structure, a vector space structure. Let's take Euler's method. What does it do? Computes a new solution from the old one, right? By just taking the vector field and moving a little bit forward in that direction. This is this method is called Euler's forward method, right? It's the first method. It's a stupid method because it doesn't preserve any structure if you have some structure in your vector field here, but it's a method, right?
Yeah.
And so this is a map that goes from your manifold, that goes from your original point on the manifold here to another point on the manifold here, right? And if your h is small enough, this and you're on, at least on if you're on a vector space, this is going to be a diffeomorphism.
Yeah.
That's what I mean.
Yeah, no, I know that, but that you can't write that on a computer.
You mean because you have rounding errors?
Well, I mean, you're talking about points on a manifold. You can't write anything on a manifold on a computer. So you have to, and then you're writing it some way on the computer, and then you're saying it preserves this structure. So I don't know what that means because it's some discrete.
Okay, so let's do it. Let's say what am I doing really? I mean, it's important actually what you say. So what am I doing? I define some sort of algorithm by some sort of equations like here, right? And then I say that algorithm. Never mind computers now. It's just an algorithm. It's just an equation that takes you from one point to when you solve this equation, you go from one point to
so
another.
Mathematically, it makes sense on this level, but it doesn't make sense at the discrete level.
So you're right. So and when I say that the method is symplectic, what I really mean is that the algorithm, mathematical algorithm that I sort of define in terms of equations, will give a symplectic mapping.
All right.
Right? That's what I mean. But then, of course, that's not exactly what we do in the computer, because we also have rounding errors. We cannot represent real numbers in the computer.
Yeah.
So you're right. That's not exactly what we do. That's what you mean with we don't have manifolds, I guess.
Well,
because there's no field R that you can define sort of coordinates for a manifold or whatever. Okay. Anyway, I'm drifting.
Well, I mean, a Lie algebra might have structure constants that are rational numbers, for example, like SL2 does. And then you could talk about rationally it would.
Yes. No, so what I'm saying is really, when I say that it's symplectic or whatever, I really mean that the algorithm defined mathematically.
Okay.
Okay. Yeah.
The Euler procedure, whatever, preserves the structure. Yeah. Okay.
Yeah. Exactly. So now let's summarize the analogs that we have. I apologize, I'm already 15 minutes late, but I'll do what I can to speed up. So so we have sort of these analogs between Euler and Zeitlin. Let's summarize them. So vorticity function, we already know that corresponds to vorticity matrices. Stream function corresponds to again a matrix, right? Everything is skew Hermitian. Now, what about the Casimir functions? So I write that this is sort of the monomial Casimir functions. It's not the only way to write them, but I sort of do it like this. So each of these Casimir functions also correspond to a Casimir function in the quantized model. And then you just take your matrix to the power k and you take the trace of that. This is going to be preserved by in Zeitlin's model. So here are more interesting things. Take the level values of some smooth vorticity function, omega. It has a sort of weak correspondence in the quantized model. I write it like that because it's weak. So it corresponds to the eigenvalues. We saw this, I sort of indicated this already. What about the eigenvectors? So once you have eigenvalues, it's natural to talk about eigenvectors as well. What are the eigenvectors of our quantized objects, of our matrices? They correspond to the level sets of the function. Weakly, again, there's some quantum effects that come into play. I will show you some numerical experience with this if you mind waiting. And in sort of interestingly, if you have, you can have point vortices. I discussed that. That's when vorticity is sort of just sits on certain points like a delta pulse. But you can also have a vortex curve where vorticity is isolated to lives on just a curve, one-dimensional curve on the sphere. And this somehow corresponds to rank 1 matrices on the quantized level. So here, just some results for from quantization theory. So this is really the first results I'm talking about here. Has nothing to do with Euler. It's just for this, generic for this type of quantization scheme. So these are some results that when you let n go to infinity, you get convergence of the L infinity norm. So this is the operator norm or the spectral norm of the matrix. So the largest eigenvalue in modulus corresponds to the largest function value. Okay. So this also reflects this fact here that the eigenvalues corresponds to the level set values. Okay. And then you have convergence in sort of other norms as well. And more generically, you have convergence of these Casimir functions. So the quantized ones converge to the continuous ones. And this is some recent work that is not even published yet. This is with a master student from Paris that I was working with. Hopefully we'll have a preprint soon. He was sort of looking at this from the Euler perspective and then proving also convergence of this energy function, which corresponds to an H-1 Sobolev norm. So you have also convergence of that. But more interestingly, he tried to look at also the geometry, see in what sense the geometry is sort of converging. So he looked at sectional curvature. So remember, once you have a Riemannian metric, we can talk about sectional curvature. And if your Riemannian metric is right invariant, it's really enough to just look at the algebra level. And then Arnold, I think, or maybe even before him, gave some formulas for how to compute sectional curvature with respect to such metrics. You can do exactly the same thing in the finite dimensional algebra. And then you have convergence also of sectional curvature. So that's nice. Somehow it sort of captures the geometry in the Euler equations. Here are some non-analogs, or if you like, they are analogs only in the weak sense or in the weak star sense. So there are some quantum effects. And in fact, I think if you mind, I will just show you a little bit how, what I mean with this. So do you see my screen?
Yeah.
Yeah, so here are some computer experiments. Here is, I've just visualized again using, you know, these coordinates, some smooth function on the sphere. It has two, again, it's just a smoothing of what you saw before. In fact, so I applied some heat flow to make it a bit smooth. And then you have these blobs here, two red ones and one negative one, the blue one. And then, so this, of course, this is some matrix, right, that represents this function here. And then I take that matrix, I compute its eigenvalues and its eigenbases, okay? And then from that, I just look at the individual eigenbases, and I think of, I look at that matrix for at some certain eigenvalue, right? Corresponding to, that I know corresponds to some negative value, so that it should be corresponding to a level set of the blue ones. What do I get? Do I get a level set? Not exactly. I don't exactly get a level set. It's more like each of these basis functions somehow represents a level set, but it's more than that. It's more like, if you like, it's like a wavelet basis, something like that, what you get. So this is a quantum effect. And how do you see this? Well, we can do the same thing sort of in a simple way. We just look at zonal flows now. Remember, zonal corresponds to the matrix being diagonal. So now I'm taking a matrix which is 0 everywhere, except at one spot on the diagonal. What do I get? I get something that is zonal, of course, and it's sort of indicated here which diagonal I took, but it's not 0 everywhere, okay? So what do I do now? I said, okay, instead of just taking one eigenvalue, I take a sort of convolution that is specified by some function. So I sort of select just some of the eigenvalues close to this value here at a certain elevation. And then let's see what I get. What I get is, now it looks more like I managed to sort of find this band here. Okay, so it means that if you just take one of the eigenbases, it's not enough. But if you take a few of them and select and sort of isolate them, then you get a nice sort of spatially, let's say, well-defined level set. And if I make this finer, it gets even nicer. Let's say if I take 15,000 as a sigma, this is a Gaussian pulse I'm using here. So now it's very narrow like that. And then you see it because this band becomes more narrow. And I can make it even finer, but at some point I get sort of, Heisenberg comes back to me. So I get some quantum effects. It's no longer perfectly, I get these waves coming back. So I think this is a sort of, these are some quantum effects we see in this model. And if I do the same thing now,
I mean,
with this,
these two things are related by Fourier transform, sort of.
Yes, yes.
Metaphorically.
Yes. So somehow you can say that, what is this? It's Heisenberg in the sense, if you want to sort of be very precise in where you are, then that somehow means that you're losing precision in where you are in the matrix, if you like.
Which is
or
the
which
which
yeah.
is one like, okay, yeah.
And here I did the same thing. So I used the same convolution, but now for some eigenvalues correspond to a few of the level sets of the blue one here. And then you see I get something which is more well-defined like this. So let's see if this is the one.
So in terms of the velocity and the vorticity, the blue circle corresponds to what?
So think of this blue circle. So I needed to take the sigma a bit smaller, and then let's see if it's well defined. So think of this this blue circle here is a matrix which has very low rank. It's not rank 1, but it's I mean n is here 500, I think, or maybe 1,000. So n is 500, let's say. Maybe the rank is 10 or 5 or something. Yeah.
Okay.
So it's very low. So most of the eigenvalues are 0. Almost all of them are 0. Just a few that are not. And then so that's what I mean in this analogy, that sort of vorticity curves, where you have vorticity on a curve, corresponds somehow to low rank matrices. Okay.
Okay.
What else did I want to show you? I think I'm almost finished now. We've been talking a lot. Yeah, okay, I didn't say anything about this. Okay, I just wanted to say something about the spectral decomposition, because that's really quite interesting. So let's, no, that's not what I wanted, sorry. Go back to the iPod. So non-analogs, yeah, I showed you these quantum effects. What about the spectral decomposition? Remember the talk from last week? I wasn't able to listen in because it was in the middle of the night for me. But essentially, as far as I understand, the question was this. So someone gives you a vorticity function, right? And then you ask the question, is there a volume preserving diffeo that transports this vorticity to something which is the steady solution to the Euler equations? Okay, and in general, the answer is no, if you work in the smooth category of functions and diffeos. And then the question is, but how close can you do it? So in the Zeitlin case, in general, the answer is yes. And the proof is very simple. It's just a spectral decomposition. Because you know by the spectral decomposition that you can take any matrix and applying some adjoint action on it by some element in SUN, and get a diagonal matrix. And the diagonal matrix corresponds to zonal flow. So it's a steady solution. So somehow, if you take the limit n goes to infinity, the Zeitlin model is some weaker version of the Euler equations. It's sort of the orbits are larger, if you like. It's some completion of the orbits you have in the smooth Euler equations.
Why do you say that?
Because somehow we're able to reach much more with these orbits. We can take any vorticity, and we can always transport it to something which is zonal. That's not true in the smooth category at all, right? I mean, if you have like a number of maximum or minimum points, for example, those who are preserved always. You cannot destroy that with a diffeo. So somehow, you know, you can do that here. And I think what happens in the Euler equations is that these are weakly destroyed. That's what the sort of weak mixing somehow.
So it's more like the Navier-Stokes. I know that's non-Hamiltonian, but I mean, the vorticity is sort of destroyed when you have a little viscosity, the structure.
Yeah, you're right. So we can reach more. That's why I say this is sort of some completion, some weak completion of the orbits in the smooth category. And in fact, this idea of having sort of a completion of the orbits, so Schneermann has been working with this, and he has an idea of doing this. And what I think, at least in one example, he computed this completion, and what he did was sort of L infinity weak completion of the orbits. And what he get is that it's characterized by the range of the function entirely. And that's also what we get here. Remember, because we're not changing the eigenvalues. Whatever we do, we can never change the eigenvalues. So the range between the largest and the smallest eigenvalue is always preserved. And that corresponds to the range of the function. So I think this is a nice way to sort of work with this Schneermann's completion idea of the orbits. But I haven't investigated this in more detail.
Well, it's interesting because the texture of the two mathematics is completely opposite, right? One is Lie
Yeah.
theory, highly developed, and his texture is extremely fractal and
I know. Yes.
general geometric analysis sort of point of view.
Yes.
So
yeah.
one's algebra and one's hard geometry analysis. Sort of, yeah.
Yeah.
Algebraic. Yeah.
You're
so
right.
It's interesting to have a connection with that.
Yeah. So maybe I'll say something about this splitting as well. So we have this Zeitlin model. And as I said, once you have this, it's natural to split vorticity into one part, which is sort of belonging to the stabilizer of P. So the stabilizer consists of all elements that commute with P, okay? So this is a linear space, so we can use the Frobenius inner product, the L2 inner product, to just project W, and we get the WS, and that gives us a canonical decomposition of our vorticity. And it's interesting to think of these things in terms of two norms. You have the entropy norms, which really corresponds to L2 in a product. So on the quantized level, it's just a Frobenius in a product. And then you have the energy norm, which corresponds to Sobolev H minus 1, which looks like this. So it uses this quantized Laplacian here. Okay. And then what I said is, it's, you know, by direct sort of computation, what you see is that by construction, entropy, sort of these two WS and WR are orthogonal with respect to the entropy in the product. But then if you look at the energy, it's sort of what is orthogonally is WR and W. Okay, so this means that the sort of energy of WS is always larger than the energy, than the conserved energy, which is. And this is also what we see in experiments. So maybe I'll show you that as well.
Isn't this a prima facie contradiction? A vector is a sum of two vectors and it's perpendicular to one, and then it's, I mean, you have two equations. It seems contradictory to me. Unless everything is zero.
No, they're two different inner products.
Oh, they're two different inner products. Sorry.
Yes. So of course they cannot. It's not with respect to the same one. Then it's not possible. Of course.
Oh, yeah,
two different inner products. But
okay.
It's still interesting. It's still interesting, and I think it's closely related to what is sometimes in physics called the inverse energy cascade. I'll show you why I think that. So here again are some plots that we're generating for the next paper. The spectrum properties of this decomposition is also interesting because it captures this kink that you always see in the spectrum. But that's not what I wanted to show you. I want to show you this. Okay, so here is the entropy plot. Here's total entropy that's preserved, right? Over time. And this is more or less the simulation that I showed you, one of these first simulations I showed you. And then initially, you look at the entropy corresponding to the R part and the entropy corresponding to the S part, right? And then what you see, it's not monotonic, but the trend is that ES goes down, right? And then ER goes up, okay? So, and remember, this is a norm. This is a norm of WR, norm squared, in fact.
But it stabilizes ER.
Yeah, it seems to stabilize, yeah. And this is somehow contradictory as well, because remember, what we're doing is we're evolving on coadjoint orbits, and those are compact orbits, right? So we should have, and it's Hamiltonian. We preserve the volume form, so we should have Poincare recurrence here. And I got a question about this last time I talked about this, and now I've been thinking a little bit about it, but I don't want to discuss that too much now.
Well, that doesn't contradict recurrence. It could be staying on a hypersurface or something.
Yeah, if you have a good understanding, I would like to.
I see. It comes. I see. It doesn't come back to the beginning.
Yeah. Exactly. Yeah.
Oh well, it's sort of going to a recurrent attractor or something. Yeah.
Yeah, there seems to be some attractor here, and I mean one possible. So I see actually two possible explanations. The first one is related to what we discussed before, that we're not actually exactly solving the Zeitlin model. There's some rounding errors going on. So we're preserving the volume form, yes, because it's a symplectic method, but we're not exactly doing that because of the reason you said. We're really using floating point numbers, and there are rounding errors. So in fact, what we're solving is somehow the Zeitlin flow with a little noise on it. If you model the rounding errors with some noise, and then perhaps it's possible to have this behavior. But I think what is the other way of explaining this is exactly the Boltzmann versus Poincaré problem. If you take particles, gas particles, and lock them in some chamber and then open the chamber, they will diffuse out, right? But according to recurrence, they will come back. But it takes so long for that to happen. So that could also be an explanation of what's going on. I'm not sure. I don't know. But what I wanted to show you is just this thing here. Also for the energy, you see the opposite behavior. So in the sense that so you remember the norm of WR in L2 is increasing, but in the energy norm is decreasing over time. In fact, it becomes very close to zero. And we think that this reflects what this inverse energy cascade somehow. That on the energy level, you really see that the sort of how do you say, that energy goes towards the big blobs, not in the small scales. If you think that this captures small scales, right? Whereas in the L2 level, it's the other way around for entropy. So yes, what else? I think I'll finish here. I'm sorry for taking so much extra time. Thanks, Dennis, also for very good questions. Let's see. Yeah, I imagine some of you had to leave.
Thanks very much, Klas.
Well, I have a question about HR and HS. You mean you just you solved the original equations just the way with your algorithm and Euler's method and all, and then you just at each time you just split W into these two pieces and study it?
Yes.
Okay.
So I really.
But then you kind of suggested before that you were using a different dynamic. You're trying to guess what the dynamics was on those.
We have derived what the dynamics look like. So we have derived the equations, Zeitlin's equations, in terms of WS and WR, but we're not using that in the numerics.
Okay.
But we have, and I think that dynamics actually tells you something about what's going on. By studying that in dynamics, maybe that can give some insight. The other thing I didn't say is, can you do this in the infinite dimensional setting? What does this WR, WS correspond to? And you can't do it if
you said you can't do it before.
No, you can't do it, but you can do it weakly. You can do it weakly in L infinity, in fact. And then heuristically, what it means, if you take this picture that eigen functions or eigenvectors correspond to level sets, then what it means is that you're taking your vorticity and you're averaging over the level sets of the stream function.
Oh,
that's sort of what this transform is doing. And in fact, that's sort of what you see if you remember in the plots as well.
Well, this is.
If you see here, you see here you see P actually. So here you see the stream function, and here is a complicated vorticity, right? But you see, if you look at WS, it's like taking this vorticity and then averaging along the level sets of P. So that's what you see here. Yeah.
Well, just that last thing you said, when you split it in infinite dimensions. And I'm a little bit talking through my hat here, but I used to have lunch all the time with Alan Kahn in the 80s. So who's the inventor of non-commutative geometry, and he uses von Neumann algebras, which is coming from quantum theory. And it's the definition is they're weakly closed. The algebra of bounded operators that are weakly closed. And then the non-commutativity creates the time evolution, and it's a whole yoga about possible formalism from quantization, which I don't understand quantization, but so maybe there's a connection between what you just said and infinity and this so-called non-commutative geometry, which is a whole field. Just a comment. Okay.
Yeah, probably there is, because I mean, as far as I don't understand quantization theory very well either. I'm using it as a tool. I don't understand it so well.
Yeah.
But there are various ways of presenting it. One, you have this geometric quantization, which is really like somehow Kähler geometry. But then there's this non-commutative geometry point of view as well, which yeah, probably overlapping at least to some extent. Yeah.
Well, I liked your whole talk, but I really liked the first part with the pictures.
Right. Yeah. Maybe
Being a topologist. Right.
Yeah, I'll go back to that. And yeah. So in fact, you know, you can. Maybe I can send a link so that you can look at these videos. If you like.
That'd be great. Yeah.
Yeah. I'll send them to the list. You know, that Vincent, the list you sent. I'll just reply on that, and then
okay.
I'll send
Wonderful.
the link. Yeah.
And Vincent, can you send out the recording to the list, please? Because some people couldn't come.
Yeah, my pleasure.
Because of the time. Some teach.
Yeah, no problem. Yeah.
Okay.
All right, Klas. Well, thank you very much.
Thank you very much. It's really fun.
Yes. Yeah. Thanks a lot for inviting me. And hope to see you at some point.
Take care, everybody. Take care, Klas.
Yeah. Thanks. Bye-bye.